All right, y'all. It's Barry. I'm here to talk about momentum, impulse, and collisions today for AP Physics. I'm going to jump right into it so that we can get rolling. So let's get to it. First, our big ideas for this unit, our big idea 3, 4, and 5, and we have covered these before, but as a quick reminder, first one here is interactions of objects with another object can be described by forces. When we start talking about collisions, we're going to have a whole lot of interactions coming up here. Big idea 4, again, interactions between systems can result in changes in those systems, and we will have momentum transfer between systems. So we'll have systems as a whole and how things move between them as well. And then big idea 5, changes that occur as a result of interactions are constrained by conservation laws. Momentum, similar to energy that we've already covered, is not just going to be created or destroyed, it's just going to transfer. So let's look into how that actually works here. So I apologize for the odd framing of this video, but I've got some extras that I want to throw in here beyond just the notes. So that's why it looks a little bit different this time. First thing, momentum. This is referred to as mass in motion. If we think about mass, we think about motion, we probably think right away about mass in kilograms and motion or velocity in meters per second, and that's exactly what we're looking at. So when an object is moving, it's said to have momentum, and that momentum is going to be measured by mass times velocity. We have this lowercase p that's going to be our symbol for momentum. Objects with momentum are equally dependent on their mass and velocity. If you remember back with kinetic energy, it was not equally proportional. Velocity was squared in that case. In this case, it will be equally proportional. So this really is just a different way of looking at the kinetic energy of an object with mass and velocity equally proportional to each other. And a reminder down here, be careful with your brakes, because if you slam on the brakes with a heavy load in a truck or anything else, what's in that truck won't necessarily stop. Its momentum will continue. So keep that in mind. All right, looking at changing momentum. If it's derived from just two quantities, it can only change if one of those quantities changes. Okay, so thinking about an example of velocity causing a change in momentum, of a change in mass causing a change in momentum, we're much more likely to have a change in velocity causing the change in momentum of an object, or something acting on it. We'll get to that soon when we talk about impulse. But velocity change is much more likely to happen than a mass change. It's not very often that mass just breaks and completely falls apart or gets much larger as it's traveling. It's typically velocity that's changing for an object. And you see that right there at the bottom. Commonly, velocity changes are responsible for momentum changes. Excuse me. Now, the other thing that could be responsible for that is an impulse. And an impulse is a specific case where a change in momentum is occurring. And it occurs because a force is applied to an object for some amount of time. That force being applied is what causes the change in momentum here. So we see a force applied for an object, a reminder that velocity has a direction because it's a vector, but we see force here times some amount of time is going to cause, and that's what that equal sign really means in this case, a change in momentum. All right. Now, if we have a case here where there's a boxer, and let's think about this real quick. A boxer here on the left, they are moving their head backwards. You see those little lines there implying they're moving their head backwards. And what that means is they're moving in the same direction as the fist that's coming toward the face there. And that's probably a pretty smart thing to do that will extend the amount of time that those two objects are in contact with each other. So the force is going to be less and applied over a greater time. And we see that down here at the bottom for a change in momentum. This one up here on the other side, it's going to have a greater force applied to during a less time because it's leaning into it. And likely the combination of these two right here, where if you don't lean away from a punch that's going to hit you in the face, it's going to cause a greater impulse and thus a greater collision that's happening there. Both these things are going to be used to describe collisions. So mass times the velocity of an object, that velocity is likely to change if a force is applied to that object for some amount of time. So an impulse applied to an object with momentum will cause a change in momentum. And as we discussed on the previous slide, it's most likely to cause a change in velocity. Now, how do these terms equal each other with weird units? Okay, so that doesn't seem like it may work right away, but a reminder, mass in kilograms, velocity in meters per second, we get kilograms times meters divided by seconds. Well, if we remember here also, force was mass times acceleration. So we have mass, kilograms, acceleration, meters per second squared. So we have one extra s on the bottom so far over here on the left, but if we multiply by that time also, we get rid of it. So they both end up being kilograms times meters divided by seconds. Now, there is no new unit that comes with momentum and impulse, okay? So if you have an impulse applied, you'll typically just see newtons times seconds. If you have a momentum of an object, you'll typically just see kilograms times meters divided by seconds, okay? So no new units for this. All right, now momentum is conserved. So during an impulse, we're going to have a transfer of momentum through a system. So some collisions happening there. A force is applied for some amount of time. There will be a transfer of momentum. And what we could do real quick here is say, okay, we have a 1,000 kilogram object at 5 meters per second, an 800 kilogram object at 2 meters per second. They collide. So there's some amount of impulse here. There's a transfer of momentum. Afterwards, this 1,000 kilogram object is traveling at 3.4 meters per second. We could determine how quickly this 800 kilogram object is traveling. So pause real quick, see if you can figure that one out. All right, now that you've paused and had a chance to figure that one out, hopefully you came back and you found that it's 4 meters per second. We can address that further in class with a lot more examples once we get to that point, okay? Now, to actually get into what collisions are, first, as shown on the previous slide, impulse is going to lead to this. And a lot of times you hear collision, and I think that right away puts you towards a car collision, right? I think that's the most common kind that we think of, and this is one with dummies inside, so don't worry that anybody was hurt in the filming of these notes. But car collisions could be a really serious thing, and it's really smart the way that people build cars now in order to keep those collisions to a minimum, okay? So first, collisions are not just cars. It's any change here where an impulse is applied to an object with momentum. So it's not just these cars colliding with each other down here, but this tennis ball, before it hit the tennis racket, had some mass and velocity, and it's now changing, even if it's just the direction that's changing. So an impulse is being applied. It's being applied by the tennis racket as it hits the tennis ball. Same thing down here with the baseball bat and the baseball, all right? An impulse applied, and that's causing that change. And I want to take a look real quick here at what I think is a very cool YouTube video that shows an impulse being applied to a golf ball as it hits a steel plate. And I think the important piece here is going to be deformation that happens as a result of this. So I'm going to jump over here. I'm going to move myself just a little bit out of the way and hit play. So again, the golf ball with a very slow-mo camera is coming in and hitting a steel plate, and you see the deformation of that golf ball before it springs back, okay? This is what an impulse can do to an object. A very high force applied over a very small amount of time is going to cause this mass to change its velocity drastically and oftentimes deform as it does that, okay? Maybe you've seen a slow-mo of a boxing match or something like that where a person's face looks kind of like this, right? And so again, we see the deformation of this golf ball. Now, what's really important here to note, especially having completed the energy unit already, is that energy goes into that deformation, okay? So while the momentum can be conserved, energy, depending on the type of collision, will not always be conserved, right? Again, we got to just watch that one more time because it's just too cool not to. All right, so I'm going to jump back over to the notes here. We're going to keep rolling. And now what we need to do is look at types of collisions. That's the important next piece in this, okay? So we're going to look at some different types of collisions. First one is an elastic collision. And I have some GIFs down here at the bottom that are supposed to be running, but I'm going to jump over to them in just a sec so you'll still get to see them, okay? But when two objects collide and remained complete and undeformed, okay, that's very important. Complete and undeformed. We just saw the deformed golf ball. And in that case, we lost some amount of energy, okay? So elastic collisions, elastic are when things are undeformed. The shape does not change. So a couple examples here. A pool ball, a tennis ball bouncing off of a wall. These are things that are going to be, a pool ball being the best example there of they collide because of their shape and structure. They don't actually have any transfer there of energy. They just have a transfer of momentum. So here we have a full conservation of momentum. And what this is saying is the mass of object 1 and the velocity of object 1 plus the mass of object 2 and the velocity of object 2. So this is the momentum of each beforehand will equal the mass times a new velocity. That's what that little apostrophe there stands for. Okay, it implies that there's a new velocity there afterwards, plus the mass of object 2 times the velocity of object 2. So the new momentum of object 2, they will be equal before and after. Okay, so an elastic collision, completely separate objects, they They collide and remain complete and undeformed. They're not broken, they're not cracked, they haven't fallen apart to any degree. And so we're going to see an example of this right here. So we have a truck coming up with its mass, velocity, and momentum shown, right? And as we see here, mass times velocity equals its momentum. We have a parked car, so no velocity and a smaller mass. And we're going to take a look real quick at what that will look like. So we have that coming in, and I love how it's called the momentum transfer trucking company here, right? So we see 30 and 20, and it collides, and then that 20 drops to 10. So this truck slows down. All right, it transfers, it loses some of its momentum. It goes from 30,000 kilograms times meters per second to 60,000 to 30,000, so it loses half of it. That means that that amount of momentum must transfer over here. And we see that that number jumped to 30,000 right there. Given that the mass of the car is 1,000 kilograms, we can determine 30 meters per second for that final velocity, because we knew that the momentum loss here must go to the momentum there, and we knew the mass of the car. Now notice, in this visual, there is no deformation of the truck or the car. And yes, I realize that is unrealistic in true terms, right? That's not the way that this would necessarily truly happen. But in this case here, that is what is happening. So we need to note that. Okay. So jumping back over here, we're going to look at the next example here. These are inelastic collisions. So we have elastic. Things are perfectly elastic. They bounce off each other perfectly. Okay, that's the best way to think about this. You think of things as elastic as bouncing. An elastic collision has two objects that perfectly bounce off each other. An inelastic collision is the opposite of that. Okay, that means they stick together. So two objects collide and continue to move on together. Then we have a collision that is inelastic. So they hit, they stick, right? So an example here, train cars coupling, right? Those cars are all separate until we put them together. And you put them together by having them very lightly run into each other, and then they have these little pieces that connect and hold them together as they continue to move from there. If a bullet hits a person, or let's say a piece of wood or something like that, and it stays inside them, then they are going to move together. Okay, so if you set up a little block of wood and you were to fire a bullet or an arrow at it, those two objects are going to travel together if the bullet sticks in the wood. And so all of that momentum that was in that bullet will be transferred to the two of them combined. Okay, and so here, looking at our conservation in this case, the mass and velocity of object 1 beforehand, the mass and velocity of object 2 beforehand, whatever their individual momentums are, will equal the total mass times a new velocity as they travel together afterwards. Okay, and we're going to see another example of that right here. So we have a mass of 1,000 kilograms with a positive velocity to start of 20 meters per second. So 20,000 kilogram meters per second in momentum. The truck here, 3,000 kilograms, negative 20 meters per second. Now notice opposite directions to start here, but the combinations before and after must still be the same. So we have, I got to wait for it to come back, apologies. 1,000 and 20, 20,000, 3,000, negative 20, negative 60,000. The combined there at the end should still be negative 40 that these two together are. 20,000 positive to start right there, negative 60,000. And so now we still have negative 10, negative 30, still negative 40,000 at the end there. And that's what we're looking for. And it's because this one slows down, transfers some momentum to this one, so it begins moving in a negative direction. So this actually has a drastic acceleration, a drastic change in velocity, right? Of negative 30 there, 20 down to negative 10, whereas this just goes negative 20 to negative 10. And this is much more massive, so that makes sense. So our numbers combined overall would be the same together. Now, in the end, we would have a 4,000 kilogram object as they are together, traveling at negative 10 meters per second. And notice their velocities at the end are the same because they are traveling as one object. They have stuck together at this point. All right, now, those are our two ideal cases. The problem is, more often than not, we're going to have less than ideal cases. And those are referred to either as partially elastic collisions, or you might sometimes see this as partially inelastic collisions. If you see partially anything, it's the same type of collision. And I've seen it worded both ways. So means it's some elastic, some inelastic, and it's a combination of the two. Okay? So partially elastic collisions do not fit in either of these categories. They typically involve some portions of the object sticking together and some being sent off separately. Okay, so you're going to have some bounce off and continue. You're going to have some stick together. You're also going to have deformation. okay? So we're not necessarily going to have conservation here. So most car accidents here, you see pieces of these cars flew everywhere, right? I couldn't help but throw in the picture of Justin Bieber being hit by an egg, and you see the eggshell and the egg pieces and everything else flying everywhere, okay? There's deformation here. There is some energy lost. And so to look at conservation in this case, there's no conservation of energy because energy is lost due to deformation, all right? In these other cases, we have conservation of energy. For the elastic, we have full conservation of energy, okay? And we will expand on that in just a moment. So let me save that to right here. So conservation of energy in collisions. For an elastic collision, kinetic energy is conserved fully, okay? So that means not only does the total mass and velocity beforehand equal the total mass and velocity afterwards, but the kinetic energy beforehand also equals the kinetic energy afterwards. And this is because there's no deformation of objects involved in the collision or coupling of objects that stick together. In inelastic collisions, that is not the case, okay? Kinetic energy is not conserved in that case. That's because some amount of energy is lost as the objects combine. Okay, so the momentum will be conserved. So here we would have our m1 v1 plus m2 v2 equals the masses combined times the final velocity, right? Just like we saw right here. That's what we're looking at there, all right? But because those masses are combined, we no longer have conservation of energy. And that's because in order for those objects to combine, some energy is lost. Whether it be the train cars coupling, well, some energy is being used to push those pieces together so that they can hook. If it's the arrow going into a block of wood, well, some energy is involved in moving some of that wood out of the way so that the arrow can fit in. Or a bullet hitting a person, well, some energy is a piece of that bullet actually striking and going into the person. Okay, apologies for how graphic some of this is. I'm sorry, but that's where we're losing energy in these cases, in these inelastic cases. So elastic collisions, kinetic energy is conserved. Inelastic collisions, kinetic energy is not conserved. Now, if we were in class, I would show y'all, and I'll probably pull it out for when we do our live sessions, but since we are remote right now, I can't show you just yet, our actual Newton's cradle, the balls that go back and forth and all the tricks that come along with that. But I'll show you in class, so we'll talk more about this then. Okay, but this refers largely to kinetic energy and collisions and how that works. Now, one thing I do need to note here is that collisions don't always happen nice and neat in one dimension. Okay, it's conserved in each dimension if we have numerous dimensions associated with this. So in a case like this, going back to our pool balls, first, if you think about this, think real quick, what type of collision was that? All right, hopefully we went right to elastic collisions, right? Because they completely bounce off each other. There's no deformation. They don't stick together, okay? But we have our two pool balls kind of coming together here. If I have one coming in just above this horizontal plane and one just below it, once they collide, they're going to move out at angles. And that's how pool works, right? It's not a one-dimensional game, it's a two-dimensional game. And so what we would look at here is conservation of momentum in both the x and the y directions. All right, so we have here m1x plus, or m1 v1x right here, plus m2 v2x. Now this one has a velocity and this one doesn't, so this term in this case would actually be 0 because this is not moving, right? Equals this mass times its new velocity in the x direction plus this mass times its new velocity in the x direction. Not the y components, just the x components, because that's what we looked at going into it. Okay? Now if we look in the y direction, we have a very unique situation, right? Because there's no y momentum here. This is just in the x direction. So what that means is mass 1 times the velocity of y for mass 1 afterwards, the velocity that this is moving up with, will equal mass 2 times the velocity with which this is moving down. All right? So no momentum in the y direction beforehand means that these momentums after will cancel each other out. All right, we'll do quite a few examples of these in class, so we'll get much more into that later. And an example of kind of what that would look like right here, you see those moving out afterwards, and you see the same thing that was shown, a little bit more blurry, but the same type thing is happening right there. All right, And in the end, that is all that we have here for momentum, impulse, and collisions. So a reminder, big ideas 3, 4, and 5. We're going to see a lot of the same things that we saw with kinetic energy, and we're actually going to talk about kinetic energy some as we do this too. So I hope you saw these in these notes. Thanks for watching.